Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning to all of our students. So for today's lecture, we are going to discuss 1.2 collision theory and 1.3 factors that affecting reaction rate. So untuk kuliah pagi ni, kita akan dikendalikan oleh Puan Siti Aminah binti Mazin. So diharapkan semua pelajar dapat memberi sepenuh tumpuan dan fokus terhadap apa yang akan disampaikan oleh Puan Siti Aminah. Okey, sebab di akhir kuliah nanti kita akan sediakan QR code yang mengandungi beberapa soalan dan semua pelajar wajib menjawab soalan tu dan akan dikira sebagai kehadiran kamu untuk kuliah pada hari ini. Okay, so kita start kuliah dengan Puan Siti Aminah.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So, hi guys. So today we will have a lecture on a topic collision theory and factor affecting reactions rate. So, in this collision theory, there is a few subtopics that we will cover. So the first one is explaining collision theory, and the second is define activation energy. The third one explain transition state theory, and the last one we will draw energy profile diagram of the reactions, for example in endothermic and exothermic process. So in collision theory, actually what is collision theory? Collision theory actually is a theory to explain the rate of chemical reactions, how fast the reactions will take place. So in this theory, we will cover three main points, which is the first one, this molecule must collide to react. And the second one, molecule must possess a certain minimum kinetic energy that we call as activation energy to initiate the chemical reactions. And the third one is molecule must collide in the right orientations in order for the reactions to occur. So here students, we have rate. As we know, from this formula, rate is directly proportional with a number of effective collisions. So, if the number of effective collisions is higher, the rate is also being faster. And the rate is inversely proportional with time taken. If the time taken is shortened, so the rate becomes more faster. So according to this theory, not all collisions between the molecule result in the formation of products. For example, we have 5 collisions, maybe only 3 among these collisions are effective collisions. So you can see here the 3 main concepts for collision theory have to remember is C, E, and O. C is collide. What is collide? Collide is reactant particle must collide in order to start reactions. E, enough energy. Enough energy means collision between particles of reactants must collide at least with a minimum kinetic energy that we call as EA for the symbol. And O is orientations. Orientation is a correct angle and orientation when these 2 molecules or more reactants is collide during, so to make an effective collisions. So these 3 things must have in order to make sure an effective collisions between the reactants is occur. So let us move to the next slide, which is we are talking about the effective collisions. So what is effective collisions? Effective collision can cause a form of products. So effective collisions must have 2 things. The first one, this collision must possess enough energy that we call effective energy. Okay, and the second one, these effective collisions must collide with correct orientations. So activation energy, EA, is definitions minimum energy that must supply or required by collisions to reactions to occur. Here, you can see the diagram of activation's energy. What you can see here, the y-axis is energy of a molecule and the x-axis is a time. All right. So here, the energy of reactants is higher than energy of product. So this is example for exothermic process. Delta H is negative because some of the reactants must release heat in order to form a product. So when we want to relate with activation's energy, what is activation energy? Activation energy is energy between reactants and this peak of mountains. Alright, so here kalau kamu nampak, this man carry out with a full sand of wheelbarrow. Here, so kalau this man have enough energy to climb up the top of mountains and the sand will throw down to form a product. But if this man doesn't have this enough energy, so the product will never be formed. So this is what we call activation. Activation energy. So all reactant actually is not 100% is converted to product if the activation is not achieved. So let us move to another example for orientations. Take a look here, the importance of orientations. We have two diagrams. So I'm focusing on our left diagrams. And this reaction actually, when orientation is not important. For example, if we have hydrogen's atom react with another hydrogen atoms, react with another hydrogen atom, and it will form a hydrogen gas molecule. In this case, the orientation is unimportant because hydrogen is the same. But when you have two or more type of reactant, for example, here you have OH minus and you have CH3Cl. Okay, so we have two type of reactants. So this thing, the orientations is important in order to form a product. Another example for orientations is here, the first one. Right, we have reactants before collisions and during collision and after collisions. So first, effective collisions. During the collision, if these two atoms meet in correct orientations, this product will form. But if these two green ball doesn't meet, okay, so during the collisions, the product will never form the two green ball as a molecule. All right. So, for example, here we can conclude that if we have two or more reactants, the orientation is important. Let's move to the transition state theory. What actually mean by transition state? We already covered about collision theory. The configuration of atoms, okay, So, configuration of atoms of the colliding species at the time of the collision is called transition state, right? So here we notice that when the reactants during the collisions we call as transition states, okay, and the species at this state are called activated complex. So what is activated complex? So activated complex is the species temporarily formed by reactants molecule as the result of the collision before they form a product, okay, also called the transition state. So the characteristic of the activated complex is it is very unstable, short-lived, its potential energy for this activated complex is greater between reactant or products. And the activated complex and the reactants are in equilibriums. So this activated complex will decompose either to form a product or to reform back the reactant. To make you more understand, let's take a look at the diagram about energy level. So we have a potential energy as our y-axis and x-axis is progress of reactions. This is the example of exothermic process. So we have a reactant here and these reactants must collide with enough energy, minimum kinetic energy to arrive the activated complex, to arrive these mountains. And after in this state, we call transition state theory, and the species here, we call activated complex, is short-lived and very unstable. It will form a product or reactant based on the orientations. If this activated complex have correct orientation, it will form product. If not, incorrect orientation, it will reform back to form reactant. And again, this process will continue. So a reaction profile show potential energy plotted as the function of the progress of the reactions. So here energy profile diagram, remember the potential energy against progress of reactions. So the difference in potential energy between product and reactant. So let's take a look here. All right. So between potential energy between product and reactant we call as enthalpy, delta H. So again I repeat, so the difference between energy reactant and product we are called enthalpy. So this enthalpy might be negative or positive depend on the release or absorb. So here we know that reactant must release energy in order to form a product. So this delta H should be negative. So reactant molecule must have enough energy to overcome an energy barrier separating product from reactants. Again, another example for exothermic process. Okay, here we have transition state, fasa transitions, and these reactants during collisions we call activated complex. So we have two types of reactant. One is carbon monoxide, one is nitrogen dioxide. These two reactants is collide, and during this transition, which is activated complex, and if the activated complex correct orientation, it will form a product. If not, it will reform back to be reactants. But if the reactant collide with the not have enough energy, so it again will reform back to be reactant. Okay, maksudnya when collide tak cukup tenaga, turun balik to form back the reactants. Okay, so here we have another example for endothermic process. So for endothermic process energy profile diagrams, what you can see here is reactant has lower energy compared to your products. So here, reactant should absorb energy in order to form product. So here delta H is positive. And the difference between reactants and activated complex, I repeat, the difference energy between reactant and activated complex we call as activation energy. This activation energy is forward reactions. And we have another activation energy, what we call as reverse reactions, when we take a difference between potential energy between product and activated complex. Right? Between product and activated complex is activation energy reverse. Between reactant and activated complex is activation energy for forward reactions. And the different energy between product and reactant is delta H. In this case, the delta H is positive. Alright, another case for endothermic process. So here we have decomposition reactions, which is we have nitrogens, sodium, okay, NOCl. We have 2 mole of NOCl, and these 2 mole NOCl will decompose to form 2 products, which is nitrogen monoxide and chlorine gas. All right. So this NOCl will collide and breaking the bond. So this energy will possess enough, if the reaction possess enough energy, which we call enough activation energy. So this reactant will arrive this peak of mountain that we call activated complex. And if this activated complex collide with correct orientations, and of course, all these activated complex will form a product. Okay, but if these reactants collide with doesn't have enough energy, lower than EA, what happens? So all these reactants are falling back to reform a reactant, and the colliding process is keep repeating. All right. So let's move for subtopic 1.3, because we already learned in 1.2 about collision theory. I hope you understand. And now we move to 1.3 subtopic, which is about factor affecting reaction rate. Okay. Okay, factor affecting reaction rate, we have how many here? Okay, 5. The first one is concentrations. The second one is pressure. The third one is temperature, catalyst, and particle size. So we will move one by one so you can understand this topic very clear. The second is illustrate the effect of temperature using Maxwell-Boltzmann distribution curve. This is a graph. You have to remember and you have to know how to explain this graph. And the third one is Arrhenius. So we will show you, okay, I will show you what is Arrhenius equations and when to use these Arrhenius equations. And the last one for this subtopic is explaining between temperature and activation energy toward the rate constant based on Arrhenius equations. All right. This is 5 factor. The first one is concentration of reactant. All right. So concentration of reactant. Generally, if we use a more concentrated reactant, if your reactant in liquid phase or aqueous phase, okay, in a solution form, if you use a more concentrated reactants, so generally the rate of reactions will also increase. So here we can conclude concentration directly proportional with rate. Next, the pressure of reactant. Okay, again, generally pressure is increased when we use a gas reactant. Okay, for example, we are compressing the container consists of gas reactants, and what's make happen is the formation of product is become more faster. So pressure of reactant in a gas phase, if you increase the pressure, the rate also increase. And the next factor is temperature. So temperature generally will increase rapidly as the rate of reactions is rapidly increased if you increase the temperature. We play with the kinetic energy. If we increase the temperature, the kinetic energy increase, the number of collision increase, so the number of effective collision increase, therefore the rate of reactions is also increased. So we can conclude that increased temperature will increase the rate of reactions. And the fourth one is catalyze. Okay, so catalyze will speed up the reactions. It not double your product. The product is still the same. The amount of product form is still the same. So what the function of catalyst is just speed up the reactions. All right. So again, this factor also directly proportional. If you adding a catalyst, the rate of reaction is also being faster. And the last factor, the fifth factor here is about particle size. For particle size, usually we are talking about reactant within solid forms. If you use a smaller size, let's say you use a powder instead of kepingan, so the surface area of powder is bigger. Okay, so now if you use a smaller particle size, the surface area bigger and the collision also being more collide. Okay, there is more collisions, so the effective collision also being higher. So here we can conclude that smaller particle size, bigger surface area, so the rate of reaction also being faster. Okay, so we go into detail about concentration until the particle size. Okay, so concentrations of the reactant. Rate of reaction, as we know, is directly proportional with collisions, but inversely proportional with time. Okay, so if the reactants or if the reactions have more number of collisions, so the probability to have an effective collision is also higher. For example, here we have two type of reactant, 2 mole of A and 2 mole of B. All right. So here the probability for the collision is 4 collisions. 1, 2, 3, 4. So the probability for the collision is 4. Among these 4 collisions, maybe 3 of them are effective collisions. So if the number of collisions increase, so the rate of reaction become faster. So we adding concentrated of A. Here we have 3 mole of A, and we remain the mole of B is 2 mole. How many collisions? So it will form 1, 2, 3 mole, and more mole mean more concentrated. 1, 2 mole of B. So how many collisions probability it will occur? So 1, 2, 3, 4, 5, and 6. So if you compare from the previous slide, this is 6 collisions when you use 3 mole of A and 4 collisions when you use 2 mole of A. So here we can conclude that more mole mean more concentrated meaning that more probability for the collisions to occur. And you have more chances for the effective collision, and also here we can conclude that the rate ration is also higher, increase. All right. This observation correlate with the rate law that have been previously discussed in the topic rate of reactions. Okay. In previous lecture, last week, I think, you already learned about rate law. So reaction rate, this is rate law, rate equal to K. We have two reactants, A with order of X, B with order of Y. So based on this equation, reaction rate is directly. If you see here, this is concentrations. So if the concentration A and B is higher, makes the reaction also higher, increase, right? But remember, okay, remember, this only for the other order, but exclude for the zero order. Okay, for zero order, rate law rate equal to K A to the power of 0. Whatever to power of 0 is 1. So actually rate equal to K. For zero order only, the concentration factor is neglected. Alright? Because how many A you are put in, so the rate is constant. Okay? Only for zero order. Okay? We move to the another factor, which is pressure. Okay, same as the concentration factor, pressure actually we are talking when we dealing with a gaseous phase. Okay, gaseous phase. Reactant with a gaseous phase. For concentration, we are dealing with reactant in a aqueous phase or liquid phase. All right. So when pressure is applied, so when we compress a container containing reactant here, when we are compressing, okay, when we are compressing, what happen is this molecule of reactant are closely apart, okay, are closely to each other. So the number molecule per unit volume is increased. So this is per unit volume. So the number of molecule per unit volume is increased when we are compressed, meaning that higher pressure increase the number of molecule per unit volume, resulting when these molecules are closely become closely, the collisions, the number of collisions, okay, are become more lah, right? So resulting more collision per second. So number of effective collision increase, okay, pressure increase, number of collision increase, and hence is make the effective collision also increase. All right, when the effective collision increase, so the rate of reactions also increase. This is the significance between pressure, compressing, number of collision until the rate of reactions. You have to know how to tell, how to drive your idea from begins until the ends. And next factor is temperature. As the temperature increase, I hope you're still listening and still focusing, because at the end of this lecture, you will answer a question between the point I given you, Right? So temperature, as the temperature increase, the kinetic energy also increase of the molecule increase. So we know temperature always directly with a kinetic energy. So when the kinetic energy increase, of course, the number of collision also increase. So when the number of collision increase, what we have here? So the number of effective collision also increase. So after you are telling about effective collisions, so you will say that after that the rate of reaction also increase. Right? Begin with the temperature, kinetic, number of collision, effective collision, and the rate of reactions. Okay, let's move to catalyst. What is catalyst? Catalyst is a substance. Every reactions have different catalysts, right? So a catalyst is a substance that increase the rate of chemical reactions. Okay. For example, before we use catalyst, maybe 2 molar per second. After we use catalyst, 1 molar per second. It may be more faster. Am I correct? 1 molar or 2 molar? Okay. Alright. Reaction that increase the rate of reaction without itself being consumed. Addition of catalyst increase the rate of reaction by increasing the frequency of effective collisions. Here, the function of catalyst, it will increase the rate of reaction. How it will increase? The first one, the function of catalyst is it will decrease your activation energy. Supposed to be the activation energy for that kind of reaction is 2 joule. When you use catalyst, the activation energy will lower to be 1 joule. So most of the reactant have enough energy, has the probability to achieve the goal of activation energy. And of course, the catalyst will maybe help with a correct orientations. All right. Catalyst. Okay. Addition of catalyst change the value of K, the rate constant. Okay. Catalyst can change the value of K. All right. The catalyst react by reducing EA. This one actually an Arrhenius equations, but I already introduced to you earlier. So this is Arrhenius equations because only in Arrhenius equation the activation energy will be calculated. All right. So we have activation energy. When you use catalyst, the activation energy will be lower. Ada discount activation energy. Okay. So guna catalyst, EA akan lower. So without EA lower, what happen? The rate of reaction become more faster. So this is diagram. We perform a reactions. One is using catalyst and the other is without catalyst. This experiment you will handle in your labs soon. All right. So when EA decrease, K also increase. What is K? K actually, or you already learned, K is reactions constant. All right. So this diagram is exothermic. Exothermic because we have reactant higher energy than product. So the enthalpy here delta H lah. Negative H is negative release. So what being here is actually this is without the first reaction here is without using catalyst EA. Maybe I put a value here 2 joule. 2 joule. So here when you use a catalyst, same reaction, but you just add a catalyst, the EA drop to be maybe 1.5 joule. So when this EA is dropped, what happened? The rate constant also being decreased. All right. So the rate of reaction also be faster. Okay. So more C and D is a product. Maybe C and D can form more faster, 5 minutes instead of, let's say, CD before. We want to form CD, maybe take 10 minutes. After adding catalyst, it become 5 minutes. So adding catalyst will lowering your activation energy. Why? Because this is used what we call alternative pathway. All right. So catalyst will give you alternative pathway with a lower activation energy. All right. Hope you understand. All right. So here again a diagram about catalyst. All right. But here we use the same graph. Okay, same graph. The first graph here, okay, the black one, yang warna hitam ni, okay, yang warna hitam ni is without catalyst, right? Then we do another experiment using the same molars, everything is the same. We just adding catalyst. So we repeat the experiment using catalyst, and what we have here is EA using catalyst is lower than before. So the time taken for the product form is shortened, but the amount of product is the same. Bilangan produk sama, cuma time taken to form a product is shortened. Alright? Kenapa EA dia berkurang? Why? Because using catalyst, it will provide you an alternative pathway. Okay? Ataupun lebih senang kita kata guna shortcut lah. Shortcut. Guna catalyst actually kita guna shortcut dalam reactions. And the last factor here is particle size. Okay, particle size. Actually, particle size, we are talking about reactant in a solid phase, right? So, smaller of size reacting particle, the greater total surface area. For example, kita ada satu sudu garam besar, kita ada satu sudu garam halus. Okay, amount dia sama mol. But we use garam halus, the reaction is faster. Why garam halus faster? Sebab surface area dia greater. Bila surface area dia greater, so platform for the reactions to happens is bigger. Okay, so dia ada surface area, platform untuk berlaku pelanggaran jadi tinggi. Alright, so the smaller particle size, the greater total surface area exposed for the reactions, and this make the frequency of collision higher. So saya nak kamu nampak point macam nak deliver point tu dari awal hingga akhir. Boleh buat dalam point form So smaller particle size. Second, you talk about greater surface area exposed for the reaction. The third, you're talking about the greater ataupun the higher probability for the frequency of collisions. That's why the fourth, you should talking about the effective collisions also higher. And the last one, the fifth, therefore, okay, and the conclude, therefore the rate of reaction also higher, right? So change in condition, what we can see here actually, when you increase temperature, this is a conclusion, this table, increase temperature, the reaction rate also increase. Okay, reaction rate also increase, and the rate constant also increase. So decreasing temperature, decrease the rate of reaction, and also decrease the rate constant. Addition of catalyst, addition will increase the rate of reaction and also increase the rate constant. Increase the pressure, also increase the reaction rate, and but the rate constant is not changed at all. Okay. Decrease the pressure will decrease the rate constant, and the rate constant is not changed. So here we can see that only temperature and catalyst will affect a rate constant. Alright. We are moved to Maxwell-Boltzmann curve. Okay, you have to know how to draw and how to explain. Okay, this is a graph Maxwell-Boltzmann. Maxwell-Boltzmann, actually we are talking about rate. Okay, an experiment with temperature. So here the y-axis is fraction of molecule, bilangan molecule having certain kinetic energy. This is number of molecule. Alright, remember y is number of molecule. Okay, and the x-axis is kinetic energy. Remember that Maxwell, number of molecule versus kinetic energy. So we have two reactions, okay, two same reaction. We just manipulate the temperature. All right. So the first reaction is T1. Okay, the T1 is, let's say we start with 50 degrees Celsius example. So we repeat the experiment with higher temperature, the same mole, the same thing, but we go to higher temperature, T2. So what happened? So the T1 dia punya graph dia naik tinggi, lepas tu dia pun turun pun habis cepat. For the T2 higher temperature dia naik steady. Dia naik steady, dia turun dia lambat. Okay? So remember, luas bawah graph adalah luas bawah graph. The area between the graph is the number of molecule. Let's say this is activation energy. Dekat sini adalah activation energy. So di sini luas sini belum lagi produk. Sini belum lagi produk, masih reactant. Only here is a product form. Okay, luas bawah graf selepas EA baru produk. So kalau kamu perhatikan, when you see here, luas bawah graf yang suhu tinggi ataupun luas bawah graf suhu rendah yang lebih besar. Kalau kita nak tengok luas bawah graf after EA. So what we can see here, luas bawah graf, the number of molecule that have higher temperature is more. Okay, meaning that more product you can form if you increase the temperature. Alright, so this is Maxwell-Boltzmann. How to explain? Okay, how to explain the area under curve, the area luas bawah graph, the area under curve represent the total number, bilangan molecule in the reactions. Okay, luas bawah graph adalah bilangan molekul. So that the area under curve for T1, kita tengok kita kamiran dalam matematik, kalau kamiran graf ni akan dapat isi padu akan dapat luas, so that the area under curve T1 and T2 is the same. Kalau kamu perhatikan, kalau kamu kamirkan T1 punya graf dengan T dia adalah sama sebab we are maintain the number of molecule, but kita nak tengok di sini adalah the total number molecule of T1 and T2 after activation energy. Sebab after activation energy, di sini baru produk form. Okay, di sini still lagi reactant. Alright, so here baru kita kata luas bawah graf T2 lebih besar daripada luas bawah graf T1. Maksudnya the number of molecule T2 with higher temperature is more than the number of molecule in T1, exceeding EA. Okay, the next point you boleh explain. At higher temperature, we are talking about T2. Remember, you always have to know how to draw this graph. Okay, how to lukis dia dua graf ni. You kena mention T2 kena besar pada T1. You kena mention di sini, you kena tulis EA. Okay, sini adalah paksi Y, formation number of molecule, ni paksi X. The shaded area, the shaded maksudnya yang berlorek ini, okay, the area under the curve shaded after EA represent the number of molecule. Okay, the shaded area represent the number of molecule with kinetic energy greater than EA. Alright. Kalau kamu nak tengok sebenarnya luas bawah graf dua-dua tu sama. But kita nak tengok shaded area, luas bawah graf shaded area, the molecule exceeding EA. Okay. So masih dalam Maxwell-Boltzmann punya penerangan, graf yang sama, explanation dia banyak. Okay. So the graph of T1 ini jangan terbalik. T1 ni bukan T tinggi. T1 ni T rendah tapi dia habis awal. Alright. T1 show that only a small fraction of molecule had sufficient energy EA to react at T1. Maksudnya sikit sangat. Sikit sangat molekul yang berjaya exceeding T1. So at the higher temperature of T2, the fraction number of molecules that have sufficient energy which is equal or greater than EA. So kat sini luas bawah graf yang merah ni lagi banyak. So luas bawah graf yang higher energy exceeding EA lebih banyak daripada yang T1. Alright, so itu adalah Maxwell-Boltzmann. You kena pandai lukis dan you explain one by one what mean the area under the curve. Alright. Again, we continue about the Arrhenius Equations. Okay, Arrhenius Equation ni adalah dia sebenarnya saintis Svante Arrhenius, selain pada dia buat ni, dia juga ada dalam topik acid base. Okay, Arrhenius. So Arrhenius ni berjaya menghasilkan equation, satu formula yang boleh relatekan activation energy. Alright. So bila guna ada soalan activation energy, actually it is hint for you to use Arrhenius equations. Alright. So what is K? K adalah rate constant. A adalah collision frequency factor. Ini nilai tetap untuk reaction yang berbeza-beza. Ini exponent. EA ni adalah activation energy. Alright. Activation energy dalam unit joule per mole. Alright. R, universal gas constant. Remember kena guna 8.314, bukan yang 0.08206. Itu untuk kalau gas. Yang ni kita nak guna energy So bila energy kita guna yang energy punya 8.314. So and the temperature, okay, saya nak emphasize di sini supaya kamu guna Kelvin. Okay, so you punya Celsius you kena add on 273. Kalau saya ni silakan 273 untuk make sure baru boleh guna Kelvin, sebab kita guna 8.314 dalam unit Kelvin. Alright, so ini Arrhenius equation kamu. Kalau let's say we draw it as a graph, here is rate constant, okay, and here is temperature. This is example of exponent graph. Alright. So susah tau nak calculate using exponent. So kita make it simple adalah kita learnkan exponent tu. Sebab bila kita learnkan exponent, it will make easier for calculations. Alright. So this is original of Arrhenius equations. Okay, kalau soalan minta Arrhenius equation, kena bagi yang ini jangan bagi yang dah learn. Ini original punya. This is original Arrhenius equations. So when we learn, okay, left and right equation, ln K, ln A in a bracket. Okay, so bila ln darab dia jadi tambah. Ln A tambah ln E negatif EA over RT. Kemudian ln E actually 1. Okay, ln E actually 1. So EA ni kuasa, so kita boleh bawa dia ke bawah. Negatif EA over RT ln E tambah ln A. Alright. So ln E ni jadi ln K. Ini EA over RT. Ln E dah tak ada sebab dia jadi 1. Ln E ni dia jadi 1. Ln A ni dia akan jadi pintasan. If you see here, kita ada dua nilai pemboleh ubah. Kita ada rate constant and we have also temperature. Remember, I already teach you that temperature will alter your K value. So, nilai T yang berbeza memberi K yang berbeza. So, kat sini kita boleh cakap, okay, K dan T adalah dua pemboleh ubah. Jadi kalau kita nak buat instead of exponent graph, kita prefer yang linear graph. So ini ln K is Y, EA over R is gradient, 1 over T is X, and ln A is dia punya pintasan Y. Alright, graph representation of Arrhenius equation. This graph, contoh this graph ni, ini Y, ini M, X plus C. So sini akan jadi pintasan ln A, ini akan jadi ln K. Okay, remember ln K, kalau data dia bagi K semua ln kan. Ini adalah temperature Kelvin, so you semua 1 over Kelvin berapa sebab kita nak 1 over T. So you akan dapat satu graf garis lurus berkecerunan negatif sebab kecerunan ini negatif. Slope dia slope negatif. So slope negatif guna Y2 tolak Y1, X2 tolak X1, dia punya gradient equal to EA over R, and these are actually 8.314. So from this graph, when you plot, you get the gradient. When you get the gradient, you will calculate, you will get your activation energy. Alright? Ini ada dalam soalan tutoran. Okay. What happen if you got two temperature, okay, two temperature, and what happened to activation energy? Alright, so activation energy is still the same. Sorry, kat mana dah ni? Kat mana dia? Okay, boleh. Okay, so thank you. So when temperature is different, the EA is still the same. Okay. But the K is different. Maksudnya bila T1, K dia 1. EA dia sama. Okay. Bila T2, K dia 2. Tapi EA dia tetap sama. Okay. Yang alter EA ni siapa? Yang alter EA ni catalyst sahaja. Alright. So bila kita subtract, kita guna matematik punya kemahiran, you akan dapat ini adalah Arrhenius equation with two temperature. So dia kata okay, T1 ini, K dia apa? T1 ini, berapa K2 dia? Diberi EA. So you boleh calculate. Okay, R dia 8.314. So kena pandai guna bila nak guna yang ni, bila nak guna satu temperature. Alright. So the last one, okay. Ini adalah relations between temperature and activation energy towards, if you looking at the Arrhenius equations. So here, temperature, when you increase the temperature, okay, kinetic energy increase, the collision increase, the reaction rate increase, okay. So everything here is also increased when you increase the temperature. But if you increase the activation energy, activation energy ni kalau ditingkatkan, maksudnya susahlah reactant tu nak mencapai produk sebab dia kena panjat tinggi bukit barulah boleh form a product. Okay, so when you increase the activation energy, actually it will make the reactant difficult to achieve the activated complex. So here the reaction rate will decreases, rate constant also decreases. So I hope you understand this lecture of collision theory and reactions, the factor affecting reaction rate. Okay, please scan this QR code to answer your questions, and we will open this QR code. You boleh jawab bila-bila pun, tapi saya harap sampai malam ni you cuba jawab lah. Okay, yang ada muat, okay, pelajar yang ada muat, yang kelas, okay, saya harap kamu jawab juga. sebab ini kehadiran. Okay, hari ini ke esok ke mesti jawab. Jangan tak jawab. Saya akan tengok siapa yang dah jawab, siapa yang tak jawab. Jangan jawab terlalu lambat. Sampai situ saja. So kita kembali kepada Puan Syafinas.
Okey, terima kasih Puan Siti Aminah atas penerangan kuliah untuk subtopik 1.2 dan juga 1.3 tadi. So diharapkan semua pelajar dapat memahami, dapat mengikuti fokus apa yang disampaikan oleh Puan Siti Aminah sebentar tadi. So diingatkan sekali lagi, jangan lupa untuk scan QR code yang diberi. Okey, so dan jawab beberapa soalan yang diberikan dalam tu dan yang ini sebagai bukti kehadiran kamu. So kalau boleh sertakan sampai malam ni. Okay, last so dan jangan lupa minggu depan, hari Rabu minggu depan kita jumpa balik untuk topik 3 iaitu electrochemistry untuk subtopik 3.1 galvanic cell. Okay, terima kasih semua. Assalamualaikum.